Today I want to tell a little bit more about the Aschenthal model about uh, Aschenthal conformal block. Uh, so, uh, formulas for which were obtained by the molecule. Let me remind what we studied the last time. We found the following phenomenon that we can consider uh, antiperiodic boson which means that this I of z is sum over half integer numbers. Uh, and uh, mm, and if we consider the normal product of this I of z's, if we consider t of z is 1/2. The commutation relation between these a's is the same. So if we consider a normal product of this i's, then components. So this expression is single valued, and components of this energy momentum tensor are O0 is 1/16 plus a sum of an in a minus n an from n equals to 1/2 to infinity, and lns are sum over 1/2 something like this. So a vacuum vector on this representation has dimension 1/16 and it's a field of dimension 1/16 in some theory with central charge 1. So O0 on vacuum so the structure of this the structure of this theory is the following: that we have some field which changes the sign of this antiperiodic current. And this field is an example of twist field, and it has this dimension. And if we so we can call this a field sigma, maybe sigma 0, maybe better. So this vacuum state corresponds to some field sigma 0 of 0, delta of sigma 0. And the question which we wanted to study the last time, but I forgot how to do this computation precisely, was what is the structure of this module constructed about this field sigma zero with the help of this bosonic generators. So, namely, we want to compute uh, so the question is what are the other fields? What are the other primary fields? So, to study this question, we can consider we can just take this character of a module generated by a half-integer boson and multiply by a Versor character. So this dimension is not special. So all Versor modules are gamma modules, and their characters is 1 over product of 1 minus Qn. So the character of the highest vectors in this Versor modules is product 1 minus Qn from n equals to 0, from n equals to 1 to infinity, over a product of 1 minus q n plus 1 half, from n equals to 0 to infinity. So like this. We can transform this expression in the following way. So we can write that wait, we again forgot the computation. So we can write that it is a product from n equals to 1 to infinity, 1 minus q n over 2, 1 plus q n over 2. Here it's this 1 over this is a character of so let me write this. So a character of the vector space generated by a minus n1 minus 1 half and so on, a minus a and k minus 1 half acting on this sigma 0. We denote vacuum in this way, equals to 1 over product of 1 minus q n plus 1 half, from n equals to 0 to infinity. And this is and this is by construction, right? Because we can take arbitrary number of each half integer modes. And we want to say that it is actually we should include this dimension q to 1 over 16. So it equals to and what we want to get is uh, sum of q to some delta i's product of 1 minus q to the power n. So we say that this module can be expanded as a direct sum of Rama modules. So we say that it equals to a direct sum of so we want to find this deltas. And let us denote this sum chi tilde of q. So it's character of highest vectors. So this chi tilde of q equals to product of 1 minus q to n over product 1 minus q to n plus 1 half. So oh, I can see what I did there, but let me try to remember. Maybe better to open this computation. Was okay. I actually wanted to compute this original character and not chi tilde. It's better to compute that one. So we can write this original character as the ratio. So we include both integer and half integer numbers in the into the numerator and divide it by a product of q2 integer powers to 1 over 16. So, oh no. Oh, we need to do to get this in. We need to get this half integer numbers in the denominator, and then we write it as a difference of squares. and I can cancel this product. So finally it gives such expression. Mm. So we'll come back to this formula, but because it also has a fermionic interpretation. But now let us write a triple Jacobi identity. Triple Jacobi identity tells us that sum of q to n squared over uh, 2 uh, t to the n sum over integer n's equals to a product of 1 minus q to the n, product of 1 plus t q to n plus 1 half. So there is such an identity which can be understood in this Bosonization picture, because maybe let us leave it as is, but its interpretation is the following. So we consider complex fermion psi star, and says that they can be bosonized. J, and we can compute the following character of Q and T equals to a trace of Q to L0, T to J0, and if we work in the space, there are two ways to compute this. If we compute it on the fermionic side, we know that a charge of psi star is +1, charge of psi equals to -1, and they have half integer modes. So it is then the product of those are modes of psi star times product of some modes of psi. So, and another way to compute this is to say that this fermionic Fock module can be expanded as sum of bosonic Fock modules. And let us look at the energies of these states. So let us draw a picture. The eigenvalue of J0 or A0. Mm, and eigenvalue of L0. So there is somewhere a true vacuum with zero charge. So it's vacuum. Uh, but we want to ask what is the vacuum with charge 1. So there should be some state here. And what are the ideas? What can the state be? What do you think? Yes. Hmm? Uh, uh, yes, but these exponentials are psi's and the psi's have some mode expansion. So I'm asking how to write this state in the fermionic language. Okay. So the question is basically how to write a state with smallest possible dimension with a fixed charge 1. So, if I write the answer, it should be obvious. So the answer is that it is psi star minus 1/2 acting on a vacuum. Because it is so if you add psi and psi star, they will cancel the total charge uh, and uh, but each of them will have some positive dimension. So we can remove at the same time a pair of psi and psi star. It will not change the charge, but it will decrease the dimension. So we can only have psi stars. And uh, so we can have psi stars with a different mode number. And the higher the small number is, the higher the dimension. So we should take the smallest mode of psi, and we get precisely the state. So is it fine? So, and now the question. So it's for dimension for charge 1, and what can be the state for charge 2? So, Oh, we should take as small numbers of psi as we can, but psi squared is 0, so they all should be different. So it is psi star minus 3 halves, psi star minus one half, acting on 0, and so on. So in this state is psi minus one half, acting on 0. And this is psi minus 3 over 2, psi minus one half, acting on 0. So and so if the charge is J0, then so J0 of this psi star psi star minus one half equals to some n, and L0 of the state equals to n squared over 2, right? Is one half, it is 2, and so on. It is a sum of half integer numbers from one half to one half plus 2n minus one half, right? So the situation is the following: we have this bosonic Fock modules growing from each point of this parabola.
I cannot have, for example, okay, because I just want the boundary in this case. If I have some mixed state, like with both psi and psi star, it will be in the middle.
Yes, yes. So, and we also know that there should be this relation between dimension and charge, because we know that L0 is J0 squared plus sum of J minus njn, J0 squared over 2. So, and we see precisely how this highest vectors of of Frey boson look like in this fermionic Fock module. So, so this other computation on bosonic side gives this expression. So it's a sum over highest vectors t to the n, q to n squared over 2 over integer n's, divided by a character of bosonic Fock module. Yeah, so it's kind of a physical derivation of Jacobi triple product. It can be derived from a study of theta functions, but I think that derivation is much more complicated. For example, this part is easy. We can just find all zeros of the theta function and write them explicitly. So we know zeros of the left-hand side because it's theta 3. And we can represent it as an infinite product which has the same zeros in T. But and we can also check that quasi-periodicity properties of both sides are the same. But a less trivial thing is to check that this prefactor is precisely this one, and mm, this is hmm? Because this is only character of highest vectors which are killed by all positive modes of boson. And to get the whole character, we should take into account that each such highest vector enters with all the bosonic descendants. So if we denote this vector by so this vector can be denoted by 2, and
for each term of the sum, I have an entire bosonic module.
yes.
Okay.
Yes. So this fermionic module is an infinite sum of such bosonic modules. So they should not necessarily be Versor Verma modules. But we are interested only in the free-bosonic structure. So the free boson or Heisenberg algebra does not have all this non-trivial properties for special values of A0. So its model is absolutely the same for any value of G0. It just doesn't enter in the algebra relations. So, are there any questions about this? Yeah. So let us use mm, this identity in our case. Namely, let us consider the following sum. Let us take square root of q instead of q. And say that t is q to 1/4. So it will be a sum of from 1 to infinity, 1 minus q to n over 2, sum from n equals 0 to infinity, 1 plus q to thank you, 1/4 plus q to 1/4. So we have this expression, and uh, and we can notice that this 1/4 plus 1/4 is 1/2, which just shifts the index of summation, and here it's the same. It also shifts the index of summation, and we get one extra term which equals to 2 at n equals to 0. So we can write this product as 2 product from n equals to 1 to infinity, 1 minus q to n over 2, from 0 to infinity, 1 plus q to n over 2 squared. And now we see that one part of this product is very similar to what we want, and another part is just inverse character of a free boson. So it is 2 product from 1 to infinity, 1 minus q to the n. Oh, sorry, it's from 1 to infinity. So, and we can also notice that this sum is symmetric in a sense that there are terms for n equals to 0 and for n equals to -1, which are 1. And so if you draw the picture for this quadratic function, then it looks like this. So it is 1 minus 1. Oh, it's 0 minus 1 minus 2, 1. So we can just cut it in two and say that sum goes from 0 to infinity. Within this, we can write this identity like product from 1 plus q to n over 2 equals to sum from n equals to 0 to infinity q to n plus 1 over 2 over 4 divided by product of 1 minus q to the n. And if we compare it with our character, then it tells us that this character of q equals to sum of something like q to quarter n plus 1/2. So these numbers which are written here are dimensions of fields which are present in this twisted boson Fock module. So 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 it turns out that if you take usual boson, it is with a fixed zero charge. It will be just a single Vernal module of Gauss norm. But if you take this twisted boson, it contains a infinite number of submodules. So this one delta i's. Uh, so we have 1/16 and another, so it's for n equals to 0. Then we have n equals to 1, which gives here 3/2, so it is 9/16, and so on. And so this corresponds to state sigma 0. And what do you think? What state can correspond to this number? Hmm?
From the fermionic point of view.
No, from no, we are working with. We went back to this twisted boson picture. So this character right in here, it is q to 1/16 divided by product of 1 minus q to n plus 1/2. So, oh, and what is the jump of dimension from this field to this one? And what is this? Mm-hmm. So, what can it be? Yes, of course, yeah, in the noted way. Sigma 1, and it is maybe maybe we can think about. I didn't think about this, but let us try to think about 25/16. It is 1/16 plus 24 over 16. So it is 1/16 plus 3/2. But here it's a trickier question because we have two such states. One is 1 minus 1/2 cubed sigma 0, and another is a minus 3/2 sigma 0. Mm. So we should actually have a descendant of this state, which is L minus 1 acting there, and L minus 1 on A minus 1 half sigma 0 will be A minus 3 over 2, A 1 half, A minus 1 half, sigma 0. So it will be 1 half, A minus 3 halves. We found that this one is a descendant of this one, and this one is orthogonal to it, so it should be something like sigma 2. Yeah, and any questions about this?
So going on with the dimensions,
Hmm?
going on with dimensions, we will have always more states with the same dimension, but only one is a factor of
Yes, of course, because we have this module structure, so yes. So, mm. So, and another observation in this case is the following. So we have this character. So we can write it in the following way. So this curve Q equals to Q to 1 over 16 product of 1 plus Q to the power n times product of n equals to 0 to infinity 1 plus Q to n plus 1 half. And it should remind us something, namely, remember that this 1 over 16 appeared in a different context. Namely, it was a dimension for a Ramon fermion, for a fermion which had minus 1 monodromy around the origin. And it appeared in the context of the Eisen model. And this is the character of NS fermion, since a real fermion with usual boundary conditions. So we can write that it equals to chi Ramon, and it equals to Q, and it equals to chi NS of Q. And um, when we see this, we realize that actually, for the case of this twisted boson, it's possible to write another bosonization formula. So here, this J, which was usual periodic J, was psi star psi. And here we can take two fermions, one of which is a real Ramon fermion, and another is a real Neville-Schwarz fermion, and say that I of Z is maybe up to some factor. I'm not quite sure. Well, maybe without any factors. just this psi, maybe with I, psi Ramon of Z, psi ns of Z. Uh, we can just we can write it in just a product because they commute between each other. So if you compute OP between FZ and FW, it will be I squared, which is -1. Well, it's clear that it is psi r minus psi r of Z. Psi r of Z, psi of r of psi ns of Z, psi r of W, psi ns of W. And they, oh, it's a good question, like what to tell about different fermions, but the safest option is to say that they always anti-commute. So we have this parents, which I will give a minus sign because we should move them together. So it equals to plus IGR. So it equals 1 over Z minus W. And here we have the same logic that OP of the psi of Z of W is correct, 1 over Z minus W squared. And this computation does not know about the global behavior of psi and psi ns, and we can only we can look at this global behavior only at the end and realize that this boson is antiperiodic. So there is such a funny bosonization, and we can construct, so if we go to high number of bosons and fermions, we can construct a lot of such funny bosonizations with an Ramon and Ines fermions. We can also take a pair of Ramon fermions and so on. But I actually wanted to tell more about this theory. So it's nice not only because of such character identities, but also because here we can compute exact formulas for conformal blocks. So, and it can be done in the following way. So, are there any questions about this? Okay, so So we want to compute, let us call it f of 0 of z1 and so on Z to N, which is a correlator of sigma 0 of Z1, and so on, sigma 0 of Zn. But in principle, what is written here is just some random correlator. We need to specify intermediate dimensions in this correlator. And we do it like this. So we know that if we collide two twist fields, we will have some field which has which has trivial monogamy for this current I of z. So if we now say that this fields collide pairwise like this. If they collide pairwise, then they form some fields with a fixed d0 charge, which is conserved. So pair of these fields produces a field which behaves as an exponential field. So we can say that sigma 0 of z, sigma 0 of w produces, well, in principle, it can produce some infinite number of such fields, but let's say that that we fix some particular channel. So it gives some alpha of w, and with some asymptotics, they have dimension 1 over 16. So I think g minus w to some power delta of alpha, alpha of w plus plus something. And then when we consider fusion of this Fibosonic field, we have a conservation law for them. So the alpha of z, the beta of w is z minus W to alpha beta up to some factor, I don't remember precisely, V alpha plus beta of W. So, so here we have some some alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, and in each vertex we have a conservation law. So it is minus alpha 1, minus alpha 2, so depending on the direction, maybe. Maybe we can put some arrows, but anyway, there should be some conservation properties, and also because of this conservation of all these charges, some of these alphas should equal to 0. So if we now uh, consider the object which I call f1, which depends on w, z1, and so on zn, which is I of z, I of w, maybe x of x, sigma 0 of z1, sigma 2n of zn. So the subject will have the following analytic properties. Maybe I should draw some picture. So it has branch cuts at any of these. Uh, we can also ask what are the asymptotics near these branch cuts. So can you tell this from the formula for I of z? Like when I of x approaches sigma 0, we can use this mode expansion of I as to compute the OP. So what will be the asymptotics?
In negative mode, kill sigma 0.
Positive modes. Yeah,
Positive,
yeah. Mode with a positive kill sigma 0. So the first non-trivial one is a minus 1/2. So, mm, so this f1 behaves like 1 over square root of like some constant over square root of x minus the I when x goes to the I, right? And the last property is this statement. So we want to fix this intermediate charges. So we introduce here the A cycles. This is A1, this is A2, A2, A3, and in total we have A n minus 1 cycles. So integral, integral of dx f1 of x z1 zn equals to integral over ai. I from 1 to n minus 1. This integral equals to alpha I times f0, right? This charges. So it's a statement that integral of dz I of z dx I of x over sigma 0 of z to I minus 1, sigma 0 of z to I, integral around these two fields. And this equals to alpha I right? So it's the action of zero mode of this globally defined field, and we act with this zero mode on the state which appears from the product of two sigma zeros. So we fix this intermediate, not only intermediate dimensions, but also intermediate Yuan charges. So since this field is single valued when we talk about the pair of sigmas, then it has zero mode, and the zero mode can have an eigenvalue. Mm. Is it okay or not?
But you can see it by decomposing the integral around 4 as a sum of integrals around the two.
No. We should do the opposite. We should say that these fields are close and they produce some fields with the trivial monodromy of this field I of z. The module which appears from the LP is a normal bosonic module with a non-twist boson. So we cannot integrate IFX around a single twist field because when we cross this branch cut from sigma 0 to sigma 0, it changes sign, and to close control we should integrate at least twice, but it is anti-periodic, so this integral will vanish. And it's just a statement that this module corresponding to sigma 0 has no zero mode. So, mm, and this can be, and this can also be shown in this picture like this. So it is a fusion of two such states and of two such modules. And here we have a module with a minus k minus 1/2 acting on sigma 0 here and there. And on this side, we have a module with just a usual with just usual boson with integer modes. But all the all these modules can be described by analytic continuation of a single field I of z. It's just a matter of a choice of a point of expansion. So we can say that we start originally from this, for example, from one of these 2 points, and consider only the continuation of it to the whole Riemann surface. So. We can also think in the opposite logic. So we can think that we started originally from. Maybe I can erase this. We can think that we started from some Riemann surface, from some hyperelliptic Riemann surface, which covers the Riemann sphere, and this branch points are the eyes. And we have some free boson on that Riemann surface. And when we project it to the Riemann sphere and remove a symmetric part, it produces this half integer boson and some non-trivial fields, which create monotony of this boson. So, like this. So this is a free field. So it lives here. And here it is a free field plus this so we remove this since this trivial and we work with this anti-symmetric boson. So partition function of this theory below can be considered as more or less partition function of a free field above, but interpretation of this partition function is different. In this case, it is some conformal block of for algebra with some specific dimensions. So is it fine? So actually, what we wrote here is enough to recover this partition, to recover this correlator F1, because we know that if we multiply it by dx, so let us introduce the Riemann surface. Y squared equals to a product of z minus zi, I equals to 1 to n. It has holomorphic differentials. Or we can geometry or homomorphic one forms. Do you know how they look like in this case? Oh, let me add. Yes, it is fine, because when z approaches zi, dz over y equals to is behaves like dz over square root of z minus zi, which is approximately d square root of z minus zi, which is approximately dy. And y is a good coordinate around this branch point, so in this differential is clearly homomorphic. So z over y is of course homomorphic. So it is homomorphic in all branch points. The only question is what happens at infinity, right? So y at infinity behaves like z to power n plus 1. And if we multiply it by polynomial of order n, no, y behaves like z to the n. If you multiply it by a polynomial of order n minus 1, it will behave like dz over z. So it will have pole at infinity. So we should take polynomial at least degree n minus 2. So right here polynomial pk, qk minus 1 of z. And k is from 1 to n minus 1. And oh, is it in? And, we can also normalize this homomorphic differentials. So we have n minus 1 a cycle on this Riemann surface. And we can normalize them such that integral of d omega k over a I equals to delta ik. K minus 1. And k is from 1 to n minus 1. So, oh no, sorry. A degree is less than n minus 2. No, they should not have so degree of this q. Oh, why did they write qk minus 1? Like it's can write in just qk. So decay of this qk is less or equal than n minus 2. Actually, no, maybe uh, let me introduce a notation using genus of this surface, because otherwise there will be too many of this plus 1s plus 2s, 2g plus 2, 2g plus 1, 2g plus 2, oh, and here now it is better. Decay of this polynomial should be less or equal than j minus 1. The number of dimension of space of this homomorphic differential equals to the genus of our Riemann surface. So we are able to present explicitly a J of them, or a G of them, and we can prove that there cannot be more. Like, the simplest argument is that we have G homomorphic differentials and G anti-homomorphic. And we cannot have more because of topological restriction. We should also have some degeneracy of this pairing between cycles and differentials, but Henry argument is of this kind. So we see that as it should be from this picture, such expression f1 of x times dx is some homomorphic one form on this Riemann surface, because it was homomorphic one form above, and it is still homomorphic below. And these conditions on the acycle integrals fix it completely, because we can just say that these coefficients are coefficients in front of canonical homomorphic differentials, front of canonically normalized homomorphic differentials. So we can say that on this f1 of x, z1, z2, g plus 2 equals to, let us multiply it by ds by d dx. And it equals to a sum of alpha k's d omega k's of x times f0 of z1, z2, g plus 2. So it's for one insertion of this field I. Right? From the analytic properties, it is homomorphic around all other points. It has this branch cuts and with such behavior at points zi's. It does not have singularity at infinity. So it is some homomorphic one form, and periods of this homomorphic one form around the branch cuts are also fixed, because we want to fix some particular conformal block with such intermediate charges. So now let us consider a correlator with insertion of two such fields. So let us consider f2 of x y z1 z to g plus 2, which is the same I of x, I of y, and so on. So its analytic properties are the same as for f1. So, for example, this property, like integral of ai dx f2 of x y etc. equals to alpha I times f1 of y, so on. But there is one extra condition. Namely, we should say something about its asymptotics when x approaches y. And we can write on this. So we know that in the leading order we have a second order pole, and coefficient in front of this pole is the unit operator. So it gives the scalar of 0. Z1, Z2, G plus 2. But the next term in this function is 2 times energy momentum tensor. T of y and so since we have such formula, we can use the following logic. We can first find f2 from some analytic properties, and then we can recover the correlator with the insertion of energy momentum tensor, which in its turn contains a derivative of our original conformal block, depending only on this and this this, and it will give a derivative of this correlator in its arguments. So let me show how it works in this case. So we need to write a formula for this F2. We can first think about this second order pole on diagonal. So there is such a thing as a Bergman differential, d omega, how to call it? Let's call it like this. Maybe better to write like or maybe properties of this Bergman differential are the following. So d omega 2 of P1, P2 behaves like, so it does not depend on the local coordinate. It is dx of P1 dx of P2 over psi of P1 minus psi of P2 squared plus something. And the integral of it around a cycles is 0. So it's also symmetric. Let's first write about these integrals. Integral in P1, or maybe. So in principle, we can try to write it. So, for example, it has explicit expression in terms of theta function. So it's a logarithmic derivative of theta function. But let us actually neglect this part, because, for example, it does not depend on the intermediate dimensions. So it's interesting, but it's a little bit more complicated than everything else. So so in this way, we can solve this problem, like to make correct asymptotics when x goes to y. But we still need to write this. We still need to fulfill these requirements, and it can be done very easily. So let us actually introduce some notation for this part. Let us call it ds. So here we write simply ds of x and ds of y. So it's the answer for this correlator. Uh, so uh, if you now want to find the energy momentum tensor, times d dy squared. So it will equal to what? We should cancel the singular part. So it will be equal to 1/2 of limit x goes to y d omega 2 dx py minus dx dy over x minus y squared. So we cancel explicitly the singularity. Plus plus ds of y plus 1/2 ds of y squared. So and we know that asymptotic behavior of this correlator, like not only asymptotic behavior, but the full expression for this equals to the following. It is uh, 1/16 z minus zi squared plus 1/z y minus zi 1 y minus zi d over dzi, acting on f0 dy squared. The move to this one. Uh, so if you want to compute a derivative of this f0 in the I, we should take we should divide both parts by dy and take residue. So uh, so df0 over dzi. Uh, so I forgot to multiply all this by f0. and here as well. So this part does not depend on alpha, and times 0. And we will not study it. So, mm, so we can say that this f0 is equal to some. So we can say that this f0 is e to some f of z1, z2, z plus 2, and this alphas times some f tilde, which depends only on z's. And the equations satisfied by this f, maybe let us call it s. No, s is used. Oh, well, let it be f. So this f solves these equations. And df over dzi equals to 1/2 residue at oh, it's better that I'm using a variable y for this position of second field, but well, let me choose choose it at least at this moment. Z equals zi, ds of z squared over dz. So this is conformal block. And this is a set of equations satisfied by its main part, which contains both dimensions and coordinates. So, are there any questions about this?
I will take just it's just a choice to call little f what depends on the
Uh,
on alpha, let's say.
hmm?
Like it's just a choice to divide between little f and f tilde.
Yes, yes. Maybe better because here big F I don't know, but mm, we will not compute it in any way. Maybe 0 tilde. Okay, so there are these formulas, and so we have these first derivatives, and now we need to reconstruct the function itself, starting from these derivatives. So it is clear that it is some function bilinear in alphas, because S is linear in alphas, and mm, mm, if you substitute this, it will be just a combination of d omega I d omega j, or d omega k d omega l squared with some coefficients. So, but anyway, there is still a question how to integrate such residue for a pair of homomorphic differentials. And so maybe I will start from guessing what should be in the answer, and then proving that it is actually the correct object. Yeah. So we define here the A cycles, but we can also define the dual cycles, the B cycles. Namely, so uh, so here it goes on the lower sheet. B3, B2, and B1, of course. B1. So they have a diagonal intersection with A cycles. Here are the only intersection points, and if we draw them on a canonical picture of torus, it will look like this: A1, B1, A1 inverse, B1 inverse. This then the same for A2, so it's a picture of a cut torus. And period matrix is given by the integral of i's homomorphic differential over j's b cycle. My definition. And non-trivial statement about this is that it is symmetric. But it's not only the statement that we need. Uh, we need a more general formula, namely, suppose that we have two differential forms, d omega and d eta, one forms. And we want to consider the integral of one of them. Eta is, by definition, the integral from some point eta of p, integral to this point p of the form d eta. It's some function. And we want to consider the following integral. So this is our surface of genus G, which is cut in this way. And we want to consider the following integral. Integral over the boundary symmetric integral over the boundary of this Riemann surface of the following object, eta of p, d omega of p. So this can be computed in two different ways. The simplest way to do this is to say that it is just a sum of residues. It's when measuring this contour inside this cut surface. But another option is to stay at the boundary and see what happens with this function. It is single valued on this cut torus because it is just some on this cut surface. It is because it is just some disk. But when we see what happens on the boundary, we can trace precisely what happens with these functions, because actually all these points are the images of the same point chosen somewhere on the surface. So when we go around the A cycle or around B cycle, this function eta changes by periods of one form d eta, by A periods and B periods of it. And if we look at this carefully, maybe I'll show this computation the next time. If you look at this carefully, we can see that it is, maybe I'll write it with the wrong sign, but and here we should have 2 pi I, sum of residues. So if we do this computation carefully and don't miss any signs, we will have a sum from k equals to 1 to g, integral of over a k d omega, integral bk d eta, plus minus, minus integral over bk d omega, integral over ak d eta. So if we apply this formula to the homomorphic differentials, one of these sums will give delta chronicle because these differentials are canonically normalized, and another will give so suppose that uh, d eta equals d omega I, d omega equals to d omega j. So they are holomorphic, so the left hand side is 0. And on the right hand side, we have sum from k equals to 1 to g. So integral of omega over in case it's delta kj, and this one is tik minus delta ki t jk. So it will equal to ij minus tji. So it gives symmetry of the period matrix. Uh, so the next time I will briefly show how to derive this identity, and we will use it in the case when one of these differentials is homomorphic differential, and another one is the derivative of a homomorphic differential, because we would like so the spoiler for the answer is that this function f is a quadratic form with a matrix given by the period matrix of the Riemann surface. So with some coefficient, it is sum of alpha I, alpha j, tij. And this is actually what we saw in the limit when all dimensions were going to infinity. All internal dimensions were going to infinity. So it was this Zyberg-Witten limit of conformal block, and in this case, this Zyberg-Witten limit coincides with the exact answer. So, do you have any questions on this? Okay, so thanks for your attention.